Hello and welcome to week 7 of the NPTEL NOC 23MA14 Algebra 2 course. And I am one of the PMRF TS for this course. My name is Shubhajit Das. And I do hope that you are also attending Ajay Prajapati's sessions. So as we keep doing it every week, we'll be solving problems based on the content done in this particular week. So as far as I understand, this week you have been studying about categories, functors and natural transformations. So we'll be doing problems based on that. And I do category theory. That is what I do research in. And so this week is really going to be interesting. So if you have any questions, you can always email me. My email ID has been provided. So maybe I'll just write down the particular week we are currently in. So this is week 7. Yeah. So as I said that I am very much interested in category theory. And so roughly speaking, category theory can be thought of as an alternate foundation for mathematics, set theory being the former one. So when you do set theory, so far whatever kind of mathematics you have encountered, it's the basic foundation is sets and mappings, right? Sets and functions. You have studied about groups, you have studied ring theory, field theory, metric spaces, topology, and all kinds of mathematics. There is always a set on which you put some structure, and you study this particular object by understanding what are the right kind of mappings of one such object into another such object. So category theory sort of takes rather the arrows or the mappings or the morphisms, it gives more importance to the arrows or the morphisms rather than the objects themselves. Okay. Now this approach, even though it might sound very weird and maybe a bit cumbersome at the beginning, but it really is very fruitful. So to understand the objects, it is enough to understand what are the arrows coming out of the objects or what are the arrows going into the objects. So this is a very deep principle in category theory. It goes by the name of the Yoneda lemma, and it's very, very, very powerful. So what it says is that if you want to know what an object is, you can just try to know what are the arrows coming out of that object or what are the arrows going into this particular object. Okay. Now the fundamental difference between set theory and category theory is that while set theory is much more interested in what objects look from an internal point of view, what are objects composed of internally, category theory is more concerned about how one object is related to another object. That is, it is interested in the relationships. The relationships here are the things that matter. And if you understand what the right relationships are between objects, you can understand what the objects are. So as you have already seen in the definition of a category, so a category is basically a collection of objects, a collection of arrows going from objects to objects, and this collection of arrows is equipped with an operation called composition, which sort of mimics the usual composition of mappings or functions as you have seen in basic courses. And there are certain axioms which you would naturally expect them to have, like associativity, existence of identity morphisms for every object, and yeah, I guess that's all. And when you are looking into category theory, objects don't have any internal structure, while we can say that a set has an internal structure, it is composed of elements, or a group has internal structure, it is composed of elements and there is some algebraic structure imposed on it. For a cat, when you are in a category, an object for you is just like a blob, right? It's just like a point. Okay, you don't know what the object is composed of internally, rather you don't care about what it is composed of internally, and as we said, you are only interested in the arrows that are present from one object to another object. Okay, so this is what the basic idea of category theory is. And as you can understand, the definition of a category, I hope you have seen it this week. The definition of a category is very closely based on It's, I mean, the definition is if you see the definition, it's very algebraic in nature, right? So whatever you do, whatever notions you will be seeing in category theory, maybe in higher courses and all those, etc., etc., you will always be seeing that everything is being defined in terms of arrows and in terms of compositions of arrows, right? So it is purely an algebraic definition in nature. Now there are certain deeper ways of understanding this as well, but we'll not digress so much right now. In particular, in this particular course, you will be seeing, or rather you are seeing categories, functors and natural transformations. So we'll focus on those objects for the time being. Okay, so the so so I have made up questions based on category theory, and since you guys have been attending Ajay Prajapati's course, I hope that you have seen the questions which were present in the assignment. So I have made up questions of my own, and let's start solving them one by one. So I do hope at the beginning that you understand what categories, functors and natural transformations are, so that we can solve problems without any hindrance. Okay, so let's look at the first question. So the first question is asking you to give an example of a category C such that number one, C has a finite set of objects, and number two says C has an infinite class of objects and each Hom set is finite. So let's first of all focus on the first one. So this is very easy, right? You understand what a category is, and therefore you understand what a subcategory is, right? So a subcategory D of a category C is a category itself such that the collection of objects is a subcollection of the collection of objects of C. The collection of arrows is a subcollection of the collection of arrows of C. And this category D, I mean the composition in this category is given by restriction. The identities of objects, the identity arrows of objects in D are those taken from the, I mean they are precisely the identities of the identity arrows of the objects of C. Okay, so this is what a subcategory is. Now we want to find a category, give an example of a category which has a finite set of objects. So you can take any category, start with any category C, let's say the category of sets. What you do is you take some finite subcollection of the objects and you take the full subcategory given by this objects. So what I mean by this is, so you take this category of sets, you take some finite collection of sets out of that, and you take all the arrows which are present in between all these in between objects of this finite collection. You can check that this will be a category, and this will be a full subcategory of the original category, and it definitely has a finite set of objects. So start with any category, take a finite subcollection of objects and consider the full subcategory given by them or generated by them. So I should use the word given, maybe given by them. Okay, so for example, you can take let's say take the category of set, consider the sets, let's say so any set will do, right? Any finite collection of sets will do. Maybe consider consider the object n. So we can take any finite collection. In particular, we can take a single collection, a single object, right? So consider the object n and take all the arrows. From n to n, that is precisely take all the endomorphisms of n. Okay, this particular object n together with all these arrows and the usual composition, that is a composition of functions, gives you a category. And you can do the same thing for any finite collection of objects. Okay, you just need to consider all the arrows that are present in between these objects. So here in particular we have taken only a single object, so we'll only be considering arrows going from this object to itself. Okay, that is arrows from this particular arrows from this particular object to itself. Yeah. So this is an example of a finite a category which has a finite set of objects. Even though, note in particular that the collection of morphisms in this category is not finite in the for this particular category N. The category with a single object N. Now let's move to question number 2. So it says that give an example of a category C which has an infinite class of objects and each Hom set is finite. Now before we go on solving this, I want to mention something in particular, that if you observe carefully, then this word class has been put in quotes, right? It's because for us a class is we don't know what a class is, right? Just as we don't know what a set is, we don't know what a class is, right? We only can, or rather we only know from intuition that a class should be something that is bigger than a set, that is so big that it is not a set, but it's still a collection of objects, some collection of objects, right? So it all depends on what foundation of set theory you are using for to talk about category theory. So there are various ways to discuss category theory, or say various logical foundations or set theoretic foundations on which category theory can be based. So one of them is, for example, something called von Neumann universes. Then there is something called Gödel-Bernays theory, and there are many other ways to interpret them. So for us, a class is something which is a big set. Okay, so a class is something which is a big set, and we'll put all these things in quotes because it's not very precise. It can be made precise, but let's not go into all those stuff right now. So we want to give an example of a category C which has an infinite class of objects and each Hom set is finite. So what is a Hom set? As you already know, a Hom set is basically the set of all morphisms going from one object to another object. So you fix two objects in your category and you look at all the morphisms going from the first object to the second object. Okay, we usually take this collection to be a set and we call this set to be Hom set. In general, however, this collection need not be a set. So given two objects, fixed objects, the collection of arrows going from the first object to the second object need not be a set. In general, we only assume it to be a class. But if this class indeed turns out to be a set, whatever that means, then we call the category to be a locally small category. Anyways, we want to give an example of a category C which has an infinite class of objects and each Hom set is finite. Okay, so this is again easy. It might seem difficult, but it really isn't. Okay, and in particular in this example I am also going to show you that so far most of the categories that you have encountered as examples are usually sets with some, the objects in those categories are usually sets with some structure, and and the arrows are usually functions or mappings. But let's see an example of a category in which the objects need not be sets. Okay, so take any partially ordered set x comma less than equal to, which is infinite. What we are going to do is we are going to interpret this particular partially ordered set as a category itself. Okay, so interpret as a category as follows. So objects of the category are elements of X. So you understand, right, that the elements in this, the objects in this case are not set. These are just elements of the set, elements of X, and morphisms, that is arrows, that is maps, in this category are given as follows. So there exists an arrow or a morphism. There exists an arrow from the object x to the object y if and only if x is less than equal to y in the partially ordered set x comma less than equal to. So given any two objects in this category, that is given any two elements of the set x, we will say that there is an arrow, or we'll take an arrow from x to y if and only if x is less than equal to y as elements in the partially ordered set x comma less than equal to. Okay. Indeed, you can check that this is a category, right? So you also need to give the data of composition. Okay. So maybe I'll leave this to you for you to figure out. So find, or maybe how should I phrase this? Okay, so maybe composition. So what is composition? So for every triple of objects you should have a mapping, right? So for all objects x, y, z in your category, you need to give an example of a composition. So you need to give a map from hom xy cross hom yz to hom xz. Okay. Now you check that there is a unique such arrow from hom xy cross hom yz to hom xz, and the reason behind this, okay, so maybe yeah, so maybe I'll write this here. Check that a unique such map exists for all objects, for all ordered triples of objects rather, x, y, z. Okay, check that a unique such map exists for all ordered triples of objects x, y, z. Okay, so I'll briefly, so maybe I'll give a hint here. So hint, see the video. So the hint is precisely this. So suppose there is an arrow from x to y, and suppose there is an arrow from y to z. So basically what we are doing is we are picking an element of the domain set hom xy cross hom yz, right? Now we are picking an element of this domain set. So suppose there is an arrow from x to y, suppose there is an arrow from y to z. So this translated in order theoretic language in the poset x less than equal to says that little x is less than equal to little y and little y is less than equal to little z. So by transitivity you already know that little x is less than equal to little z, so that there is a unique arrow from x to z as well. And what you do is you take this pair of arrows, take this pair of arrows in hom xy cross hom yz and map it to that particular unique arrow from x to z. Okay, so this is your composition. Now certainly there might not be arrows from one object to another object in a category, right? That is, in other words, some hom sets might be empty. That is, given to objects a and b, it could happen that the set of arrows from a to b is empty. That could perfectly happen. And in this particular case, that is in the example that we are talking about, it could happen that some element in the poset, let's say little x, is not comparable to an element little y, so that there is no arrow from x to y. Okay, so the hom set hom xy can be empty, perfectly empty. So hom xy, if hom xy is empty, then the domain is empty, and you know that there is a unique map from the empty set to any set, right? So again you have an arrow for this triple of objects x, y, z. Again hom yz could be empty and still the product would be empty, so that you get a unique map from the empty set to hom xz, right? Now what would happen if hom xz were empty? It could happen that there are no arrows from x to z. Okay, but if there are no arrows from x to z, it definitely has to be the case that neither x, it definitely has to be the case that either x is not less than equal to y or y is not less than equal to z, because if both of them this would hold, then x should be less than equal to z and there should be an arrow from x to z, right? So my point in all these in this entire argument is that what ensures you properly that there is a composition map for every order triple of objects, the fact that ensures you is transitivity of the order. Okay. And what are identity arrows? So identity arrows are given by the composition data, because you know that once you have a composition, identity morphisms for an identity morphism for a particular object is always unique, right? So identity is given by, so what ensures that given an object x, little x in this category, there is an arrow from x to x, which is your identity arrow. The fact that assures you this is basically reflexivity. So given by reflexivity. Okay. And you can finally check that this is indeed a category. So check that this is a category. Now the collection of objects is infinite because we took the partially ordered set to be an infinite poset. Okay. And for any two objects, little a and little b, you observe that the Hom set from A to B, that is a Hom set of all morphisms from A to B, is a finite set, namely that it can either be empty or there is a single element, in which case A is less than equal to B, right? There is a single arrow from A to B, right? Which means that we do have an example, an appropriate example which answers the question. Which answers the question. And by the way, you observe that this is a special case of a category. I mean, this is a very special category in which for any two objects A and B, the Hom set Hom AB is either empty or there is an arrow. There is exactly one arrow from A to B, right? That is, the cardinality of the Hom set Hom AB is less than equal to 1. There is at most one arrow from one object to another object in this category, right? And that is why this category is also known as a thin category. Okay. So yeah, so we have answered the first problem. Let's move on to the next question. Okay, so the next question is about functors. Okay, so we wish to show that this particular assignment as given here from set to set, defined by sending any set A to its power set and sending at any morphism or arrow in this category, let's call it little f, to the corresponding pullback arrow, right, from the power set of B to the power set of A. We want to check that this particular assignment is actually a contravariant functor from set to set. Okay. So what do we need to understand that it's a contravariant functor? Well, clearly we see that this functor f reverses the direction of the arrows, right? So if in the domain category you have an arrow from A to B, then in the codomain category you have an assigned arrow which is from the image of B to the image of A, right? So this functor reverses the directions of the arrows. So if it is a functor, it will be contravariant. That much we know. So in order to check that it's indeed a functor, it's indeed a contravariant functor, what we need to see is that this f actually respects the category structure or preserves the category structure, which in other words means that this f preserves compositions and identities. So that is all that we need to see, and this is again very, very easy to check. So let A to B, F and B to C, G be morphisms or arrows, maybe be arrows, that is set functions. A and ABC are sets and F and G are functions or mappings. Now what is your f of G composed F? F of G composed F is G composed F, I mean this pullback, right? So what does this do? This is a map from 2 to the power C to 2 to the power A that sends any subset S of 2 to the power C onto G composed F inverse of S, right? Clearly. Now for any S in 2 to the power C, we understand that G composed F inverse of S is equal to F inverse of G inverse of C. This is a very trivial exercise in set theory that you have seen earlier. And what is this? This is the pullback of G inverse S under F, which is equal to the pullback of S under G under F in that order. Okay. And what is this therefore? This is just F bar composed with G, F R, this composed with this acting on S. Okay. So that what you have is capital F of G composed F is equal to capital F of F composed with capital F of G. Okay, for all F and G in set, for all arrows F and G in set. So what we understand here is this, that this capital F actually preserves composition. This capital F map that we have given here from the category set to the category set, this capital F preserves compositions, right, up to a reverse, up to an interchange of order. Okay, it preserves composition, and we finally need to check that it also preserves identities, and that's very easy for any object C in set. Okay, capital F of 1C, which is the identity, capital F of 1C, which is the identity morphism for the object C, right? Capital F of 1C is just 1C, the pullback, corresponding pullback map, which is from 2 to the power C to 2 to the power C. What does it do? It takes any subset S of C and sends it to 1C inverse of S, right, which is just S, because 1C is the identity map in the category of sets for the object C. So this is just 1 of 2 to the power C. Okay. Hence capital F also respects arrows besides respecting compositions. Thus what we have is thus capital F is a contravariant functor from set into set. So we have established this exercise that capital F is a contravariant functor from set to set. Okay. Right. So we can move on to the next problem, but if you have any questions, you can always ask me. So the next problem is about determinants. Okay. So I hope that you understand that what natural transformations are, right? So the basic idea is this, that whenever you in mathematics you study a new kind of mathematical object, you are always interested in understanding whether there is a right notion of a map from one such object to a like object, right? So we asked this about categories themselves, and we saw that for categories the right notion of a mapping of one category into another category is the notion of a functor from one category to another category. Again, functors can be thought of as objects in their own right. And now since you are studying category theory, you know that objects can be anything, right? It's just a primitive notion, right? You can think of it as a blob or something. So functor is also an object in its own right, so that we can ask the same question again, that whether there is a notion of a map from one functor to another functor. And indeed there is, and such a map is called a natural transformation. So so what I was saying is that yeah, so categories are objects in their own right, and so categories are objects in their own right, and a map from one category to another category is called a functor. A map from one category to another category is called a functor. Again, functors are objects in their own right, and a map from one functor to another functor is called a natural transformation. Okay, so you understand what natural transformations are. I hope you have seen the definition. What we want to do right now is to interpret determinant as a natural transformation. So what I mean by determinant here is the usual determinant that you know, determinants of matrices. We want to figure out how determinant itself can be thought of as a natural transformation. So to understand it as a natural transformation, you need to understand what are the right functors for which determinant is a natural transformation from the first functor to the second functor, right? So we need to find out the functors first of all, and even before that, we want to find out what the categories are. And very interestingly, this was also the approach taken by mathematicians, in particular Maclean and Eilenberg, when they first started writing category theory. So initially in topology, there was the notion of natural equivalences or natural isomorphisms, and people then wanted to find out, or rather make precise, this particular notion of something called natural. That is, they wanted to define, in other words, what is a natural transformation. And to do that, they needed the notion of a functor. So they defined what functors are. And even before that, they needed the notion of a category. And that is how category theory started. So let's quickly try to see how determinants can be thought of as natural transformations. So consider the category ring. So what I mean by ring here is the category of all rings with identity and unital ring maps, and the category mon. So mon here stands for monoids. So I hope that what you know what monoids are. So monoids are, as you understand, monoids are sets together with a binary operation defined on them, which is associative, and there is an identity element for the operation. Okay? So monoids are semigroups together with an identity identity element. And it turns out that monoids are very particularly interesting in category theory, and a lot of different notions in category theory are actually some incarnation of the notion of an ordinary monoid. Okay, so we don't need to digress, as I said. So we'll just so let's move on. Yeah, so we consider the category ring of all rings, and we consider the category of all monoids. So the objects are monoids in mon, and the morphisms or the arrows in this category are precisely monoid homomorphisms, that is mappings of one monoid, that is a mapping of one monoid into another monoid that preserves the monoid structure, preserves the monoid operation. Okay, so we considered the functors. Just a minute, maybe I am not very size in this. Yeah, we can sort of say interpret this in various ways. We can sort of distort this particular picture slightly, and rather than considering the category ring of all rings, rather than considering the category mon of all monoids, we can in fact consider the category of all consider the category of all groups, let's say. Yeah, so even though the previous picture would hold, but this is slightly more interesting. We consider the functors. So first functor is, so from ring to GRP, we have this functor. Oops, we have this particular functor, which is your okay, maybe I'll try to draw a better picture. Okay, so let's write it here. Yeah, ring to group. So we call it uh, so let's say GLN. So what is GLN? GLN is that particular functor that takes a ring and maps it onto the particular group which is GLNR. Right? You know what GLNR is? The group of all invertible n cross n matrices. Right? You can check that this is indeed a functor. I hope this is. So we have a ring map from R to S, and you should get a map from GLNR to NS. So what should that map be? So you take a matrix and you just apply F to each of the components, but there is a problem, I believe, here. Or is there? No, there is not a problem, because if the original matrix had non-zero determinant, can it happen that this particular matrix has non-zero determinant? So F was a ring homomorphism, and it could happen that F takes a non-zero element onto a non-zero element, onto a zero, right? Onto zero, right? It could happen. I think I'm missing something here slightly. GLNR, right? Okay, so yeah, right. So yeah, GLN, yeah, I should be very precise here. GLNR, yeah. So GLNR is not the group of all matrices. Yeah, yeah. So GLNR is a group of all matrices which are invertible, right? It's not the fact that the determinant is non-zero. We are interested in matrices which are invertible, right? In other words, their determinant should be a unit, right? Exactly. And a ring homomorphism should map a unit onto a unit, because it's a unital ring homomorphism. That much we have assumed for the category of rings. So GLN bar or GLN dot, this is your first functor, and you take another functor which is the group of units functor, right? So you understand that to define a natural transformation from one functor to another functor, the functors should have the same domain and they should have the same codomain, right? That is, the two functors that we are talking about should be parallel functors. That is, both functors should have the same domain script A, which is a category A, and both of the functors should have the same codomain script B, that is a category script B. Okay, so both functors have to be in the same direction, that is both functors have to be parallel, right? That is, both functors should have the same domain A and they should have the same codomain B. Okay, and you talk about a natural transformation from one functor to another functor. Okay, so these are our functors. Now we want to understand how determinant is a natural transformation. So consider date, or maybe det n would also do this notation, but yeah, we don't want to make it clumsy. So consider det, which we define to be a natural transformation from GLN dot to the functor, to the group of units functor. So a natural transformation, as you can see here, I hope you already know this, that a natural transformation is denoted by a fat arrow. Okay, we could also write it like this, I mean just a simple arrow, or sometimes a simple arrow with a dot, but it is more common to denote it by a fat arrow, and there is also a reason behind this. We'll not get into all these things, but yeah, so we define this natural transformation det. So what is the data of a natural transformation? So if you can recall, a natural transformation from one functor to another functor is a map that assigns to every object of your domain category, which in this case is ring, a morphism in the codomain category, which in this case is group, in such a way so for an object C, The corresponding associated morphism should be from FC. So it should be FC to GC, this morphism, and you should have a naturality square, right? I mean, uh, for every morphism in the first category, you should have a corresponding commutative square or a commutative diagram. Okay, so I think, yeah, Chaitra, hi. Yeah, so you guys are learning category theory this week, right? So what all has been covered? Can you give me a rough sketch? Categories, functors, and oh, so you haven't studied natural transformations as of yet. Oh, so okay, okay, I see. So that will be taught in the next week. Okay, so in that case, I guess this particular exercise won't be much helpful because you haven't studied what natural transformations are. But maybe we can discuss what natural transformations are because I have based many exercises on that, on those things. Okay. So do you know what initial and terminal objects in categories are? Oh, you know. Okay. So was it taught in the course this week? Yeah, yeah. I'm sorry. Yeah. So what is an initial object in a category? Can you define it once for me? Uh, what is an initial object? Arbitrary object. Yes. So an object I is initial if for any object A in the category there is exactly one arrow, that is there is a unique arrow from I to A. And dually you know what terminal objects are. So you have studied dual categories this week, previous week. Opposite categories or dual categories. Okay, fantastic. So you know what duality means, dual notions mean, right? Yeah. So and did you study what monomorphisms, epimorphisms are? Okay, that's fantastic. So a lot of stuff has been covered. And did you study what products, co-products are? Products in categories, you understand? Okay. So all of this has been done in the course, right? Or you have self-studied? Okay, fantastic. So yeah, so that means we are in a good place. So I'm a category theorist basically. That is why I'm very interested in all these things. So anyways, so since you understand what initial and terminal objects are, maybe it would be a good idea to solve problem 6 and maybe you can help me. So what we want here is to find initial and terminal objects in the category in this following categories. 4 categories I have mentioned here. We want to find what initial and terminal objects in these categories are. So before that, just tell me one thing. So you right now you mentioned what an initial object is. So does it imply in particular that an initial object, if it exists in a category, has to be unique up to isomorphism? Yeah, that is, it's because of the universal property of the initial object, right? And dually you have the same result for terminal objects as well. Okay, so maybe you can, so you understand what the category of sets and mappings are. So can you tell me what an initial object would be in the category of sets? Empty set, right? Why? but 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 the question is about existence of an arrow, right? Existence of a unique arrow from empty set to any set. And if you I mean, you know what a mapping is, set mapping is, right? You know that a mapping from one set to the second to another set is some kind of, let's say in quotes, rule, some kind of rule that associates with every element of the first set a unique element of the second set, right? If you take this definition, then you understand that for any set A, there is a mapping of the empty set into the set A, right? Why does there exist a mapping? Because the empty set is empty, it doesn't have any elements, right? So you need not associate anything to an element of the empty set, right? So vacuously speaking, there is an arrow from the empty set to any set, right? You understand what vacuous means, right? Yeah, so a vacuous statement is something that is true for all the elements of the empty set, right? And since the empty set doesn't have any elements, so any statement which is made in general about the elements of the empty set is true. Okay, so if I say that all the elements of the empty set are blue in color, this statement is true, because if it were false, then we can find an element in the empty set which is not blue in color, but that is a contradiction because the empty set doesn't have any elements. So yes, you are right, there is an arrow from the empty set to any set, and in fact the arrow has to be unique. This also is vacuously true, because if two arrows were there from empty set to some set A which are different, then these two arrows need to be different on a single element of the empty set, on some element of the empty set, which is a contradiction. Okay, so in the category set, so this is number one. So as you said, in the category set, so maybe I'll just make a table. So this is our category, this is our initial object, and this is our terminal object. So for set, as you mentioned, an initial object is an empty set. So what is a terminal object in this category? Does there exist an object that is a set in set, or maybe a better way to phrase this is this, that does there exist a set T such that for any set X there is a unique arrow from X to T? Okay, power set. So there is an issue here, right? Because power set has to depend on some set. It has to be the power set of some set, right? So, but the terminal object has to be a fixed object, right? So power set has to be discarded as an option because it doesn't make much sense. So what do you think can a terminal object be? Does there exist such a set T such that for any set X, whatever X you take, there is a unique arrow from X to T, unique mapping of X into T? Okay, first of all, tell me, can the empty set be a terminal object? We understand that it's an initial object, but can the empty set be a terminal object? Because given any non-empty set X, there is no arrow from X to an empty set. So it can't be a terminal object. So what can be a particular terminal object in this category? This is easy, you need to think a bit. What set is there such that no matter whatever X set you take, there is a unique arrow from X to this particular set? So what ensures you that there is always a unique arrow to this particular set? Let's put this terminal object into a black box. What can ensure that there is always a unique mapping from any set to this black box, to this particular set? So maybe, so can it happen that this terminal object, whatever it is, can it happen that it has two elements in it? Because if it has, then you already have two different mappings, right? You can take two constant mappings, right? But you want a single mapping. Yes, it has to be a singleton. So you take any singleton set which contains a single element, any set X, and so you take any singleton set, and no matter whatever X you take, there is always a unique arrow from X to this singleton, right? You map everything to the single element. And we already understand the terminal objects. So this is a category theoretic statement that all terminal objects are isomorphic, right? So you take any two singletons, you already understand that they are in bijection, or there is an isomorphism, right? They have the same cardinality. So any singleton will be a terminal object in this category. So next, let's look at GRP, which is a category of groups and homomorphisms. So what do you think an initial object in this category will be? Very good, trivial group. Because group homomorphisms always need map identity element to identity element. So if the domain group has only identity, there has to be a single map. And what is a terminal object in this category? What can be a terminal object in this category? Again, trivial group. Yes. So you understand something interesting happening here, right? Which is way different from what happened in the case of sets. That is, in the case of groups, trivial group is both an initial object as well as a terminal object, right? And a category, I mean an object in a category which is both initial as well as terminal, is also sometimes called a zero object. So a trivial object, so that means the trivial object is zero object in this category. So we call such an object which is both initial as well as terminal to be a zero object. And very interestingly, even though this is not, I mean, part of the course and all that, but once you have the notion of a zero object, I mean, once you have a zero object in a category, you can very much define what kernels, co-kernels of maps are, and you can do much of algebra once you have the notion of a zero object. I mean, once you have a zero object in your category. But we don't need to digress that much. Let's focus on our next example. So FLD, which is a category of fields and field morphisms. So what do you think an initial object in this category would be? Okay, even before we deal with fields, let's talk about a larger category, ring, which is a category of all unital rings and unital ring homomorphisms. So the category of fields, as you understand, is a subcategory of the category of rings, right? Okay. So in the category of rings, what is an initial object? This is interesting. Do you know what algebras are? Algebras over a ring. Yes, good. So something like modules, but the module should have a multiplication structure on it as well, or a ring structure on it. Yeah, good. Fantastic. So I am not asking you to keep all those pictures in mind right now, but what can be, I mean, an initial object in the category of rings? So can we think of a ring as an algebra itself? So it is an algebra over what? Over itself. Yeah, that's true. That's very much true. But this is not what I'm looking for right now. I'm trying to understand what an initial object should be. So that object, whatever it is, shouldn't be a fixed object. It should not depend on any object. So is there some fixed ring over which any ring is an algebra? Okay, discard the multiplication. Focus on just the group structure. So you know a ring in particular is an abelian group, right? So can you, so once you discard the ring structure from the algebra, what you are left with is just the module structure. So is an abelian group a module over some ring? Over Z, right? And it turns out that any ring therefore is an algebra over Z. Once you again plug in the multiplication structure, the ring becomes an algebra over Z. So an alternate way of defining an algebra is this, that at least for commutative rings it's this, that there should be, so given a ring A, an A algebra, that is an algebra over A, is a ring B together with a ring map from A to B. You can check that there is always a ring homomorphism from Z to any other ring with unity. So Z will be your initial object. So just to confirm that we are sort of saying the right thing, so take any arbitrary ring A. You want to give a map from Z to A. What map should you give? You want a ring map from Z to A. So what map can you give? So these, so we are inside the category of unital rings and unital ring homomorphisms. So the ring map should in particular send 1 to 1. Okay. So, and since it's Z, which is generated as a group or as an abelian group by 1, so trying to define a ring homomorphism, which is in particular a group homomorphism, it is enough to define it on 1, right? And you know what the image of 1 has to be, because it's a unit, it has to be a unital map. So you send 1 to 1 and you extend it to n dot 1. You map n to n dot 1. You can check that this will be a well-defined ring homomorphism of Z into A. And since the map is already determined by where it takes 1 in particular, and the right kind of maps that we are looking here are unital ring maps, so there has to be a unique map from Z to any ring A, which in other words says that Z is an initial object in this category. And if you sort of if you see it very carefully, this is actually how characteristics of integral domains or rings in general are defined, right? So you understand that the characteristic of a ring is some integer, some prime number, or I mean, yeah, it has to be defined in two different ways. I mean, two different steps for characteristic 0 and positive characteristic. But it is always, for positive characteristic, it is always some prime number p such that p dot 1 is 0, right? Now, what actually says, I mean, what actually says that every ring or every integral domain has a characteristic? It is basically given by the unique map from Z to your ring R. Okay, Z is an initial object. There is a unique map from Z to R. You just investigate the kernel of this map. If the kernel is 0, which means that the map is injective, then your ring has characteristic 0. And if the kernel is non-zero, which means that the map is not injective, you just since Z is a PID, you look at the you look at a generator of this particular ideal of kernel, and you accordingly define the characteristic in that case. Okay, so this is precisely how characteristics are defined. So the point is not to stress how characteristics are defined, but the fact that Z is an initial object in this category, in the category of rings. Okay, so Z is an initial object in this category. What is a terminal object in this category? Yes, and there is a question here. We are talking about rings with unity, but does the zero ring have a unity? Yes. So zero ring. So you understand, or you rather see that something striking is happening here. While in the category of groups, both I mean trivial group was both initial as well as terminal, that is it was a zero object. In the category of rings, which is somewhat similar to groups, not somewhat I mean in a very crude sense, rings, in the category of rings however you see that the zero ring is not an initial object, but it is definitely a terminal object, and the initial object is z. So can you give me, I mean, can you give me a reason why zero ring is not an initial object? I mean, of course, we understand that Z is an initial object and therefore any initial object has to be isomorphic to Z. The zero ring is not isomorphic to Z, so we are done. But can you give a much more deeper reasoning behind why zero ring can't be an initial object? Basically, because a ring homomorphism has to take 1 to 1, right? And if you take a non-zero ring, then in that non-zero ring definitely 0 has to be different from 1, because if 0 is equal to 1 then the ring becomes the zero ring or the trivial ring. So in your non-zero ring R, 0 is not equal to 1. Now you want a map from the zero ring to R, so 0 has to be mapped. 0 is now 0 in the domain is both an additive identity as well as a multiplicative identity. So it has to be mapped by the ring homomorphism to something which is both additive identity as well as multiplicative identity in R, but they are different, right? So you can't have a map. Is it okay? Okay. And finally, we focus on a smaller subcategory of rings, which is the category of fields. It's a full subcategory of rings, full in the sense that whatever objects you are taking from the category of rings, you are including all the morphisms between those objects. So my point is that every field homomorphism is in particular, I mean every ring homomorphism between fields is a field homomorphism. Okay, so it's a full subcategory of the category of rings. Now what is an initial object in this category? Certainly you know that Z together with its usual addition and multiplication is not a field. So you can't have Z as an initial object. So what can be an initial object in this category? This is interesting. What can be an initial object in this category? So you know that for something to be an initial object, regardless of whatever object, arbitrary object you take, there has to be a unique arrow from the first object to this arbitrary object. So in particular, there has to be an arrow, and moreover, it has to be unique. So is there a field F such that given any field E, there is a unique arrow from F to E? You know in particular that all fields have a certain characteristic, right? So can there exist a map from a field of, sorry, is it ZP? Did you ask whether it can be ZP? Okay, tell me something, that can there exist a ring map or a field map from a field of one characteristic to a field of a different characteristic? Suppose F is a field of a certain characteristic and E is a field of a different characteristic. Can there exist a field map from F to E? You know that if it is a field map, since fields have no honest ideals, so this map has to be, since it takes 1 to 1 as well, it has to be an injection. So if F and E have different characteristics, can there be a field map from F to E? Why? Why is it that? Why is it the case that there is no field map from F to E if F and E have different characteristics? Because otherwise F would be inside E. F would be, F would be a subfield of E, right? But if something is a subfield of something, then they should have the same characteristic, right? You can prove this. You can do this in other ways as well. You assume that the characteristic of F is some P, and then P dot 1 is 0, right? Which would mean that P dot 1 is 0 in E as well. But that would mean that P is a characteristic of E as well, which is a contradiction. And you argue for the 0 characteristic case as well. So anyways, so the point is, if you take the category of all fields and field homomorphisms, then the Hom set, the Hom set Hom F comma E, where F and E are fields of different characteristics, is empty, right? Now if this category has an initial object or a terminal object, let's say an initial object is F, then given any arbitrary field X, there is a unique arrow from F to X, right? But what would happen if X has different characteristic than capital F, right? There can't be an arrow. Every field has a characteristic. Okay. So the point is that this doesn't exist. There is no initial object. Doesn't exist. Okay. Okay, so we can, yeah, all 4 are done. 1, 2, 3, 4. Okay, now tell me, since you mentioned that you know what monomorphisms and epimorphisms are, so can you tell me what is the definition of a monomorphism in a category? Yeah, so can you tell me what is the definition of a monomorphism in a category? Okay, so okay. So let me write it. So F is an arrow from A to B. We say that this arrow is a monomorphism if so we take an arbitrary we take a morphism in a category. We say that this morphism is a monomorphism if F is a left cancelable morphism, right? So what I mean by left canceller, so if you consider the collection of all morphisms, then you understand there is a partial algebraic structure defined on it, right? You can compose morphisms, but only those ones such that the domain of one coincides with the codomain of the, the codomain of one coincides with the domain of the next one, right? So the point is that this is in a sense an algebraic structure, and once you know your algebraic structure, what you are interested in is finding the elements which are, let's say, invertible, or more generally which are cancelable, or rather one-sided cancelable, left cancelable, right cancelable, and all that. Now monomorphisms are precisely morphisms which are left cancelable. Okay, so what I mean by this is that whenever, so F is a monomorphism if F is left cancelable, which means that whenever G composed F is H composed F, this would imply, sorry, I took F on the right. Yeah, whenever F composed G is equal to F composed H, this would imply that G is equal to H. That is, you can cancel F from the left. Okay, so of course, provided that these compositions make sense and all that. So a better way to phrase this definition would be this, that F from A to B, a morphism F from A to B is a monomorphism if for all objects C and for all parallel arrows from C to A, so GH, let's say, this equality F composed G is equal to F composed H will imply that G is equal to H. Okay. This is for all C and for all G and for all H. Okay. This is the definition of, if this is the case for all objects C and for all GH, then the arrow, fixed arrow F is called a monomorphism, right? Okay. and dually you have the notion of an epimorphism. So you understand what the dual of a category is, right? So can you give me a very short description what the dual of a category is? What? Yes, exactly. Arrows are reversed, right? So the objects of the dual category are the same as the objects of the original category, while that is, but the arrows in this dual category are in the opposite direction as that of the original category. So the arrows of the opposite category are the same as the arrows of the original category, but written in the reverse direction. The direction of the arrows is reversed, and accordingly composition has also is also to be reversed. Okay, and if something is left cancelable, therefore in C, then what should be the corresponding arrow in C of B? Yes, right, cancelable. So what I mean by corresponding arrow is this. You know that uh, the collection of morphisms from A to B in C is equal to the collection of morphisms from B to A in C op, right? So in other words, what I mean by this is there is a bijection from one set to another. Let's call the image arrow of F to be F op. So if F is a monomorphism in C, then F op is an epimorphism in C. So the dual notion of a mono is AP. Okay, by the way, were you taught sub-objects and quotient objects? Okay, so I guess that won't be there in the syllabus because it's a bit detailed. I guess category theory will be, I mean, it will be going on for 2 weeks only, right? Tell me something. So you had category theory lecture in the previous week, and you will be having a lecture in this week on, I mean, on which day? Oh, okay, sorry. Yeah, yeah, it's weekly recorded. Yeah. So yeah, and yeah, so I saw the schedule, and so so only for 2 weeks you'll be having category theory, and then after that you will again get back to algebra. Okay, so I guess the next week they'll be teaching you what natural transformations are, which are maps between functors. So everything, so there you should always expect the notion of a mapping from once one, I mean, whenever you encounter a mathematical object, you always are interested in knowing what an arrow from one such object to another such object would be. What is the right notion of a map? And since functors are objects in their own right, so there is a notion of a mapping of one functor into another functor, which is called a natural transformation. That's all. So we'll be studying natural transformations next week. I mean this week. So that we'll be discussing them next week. But yeah, so you know what monomorphisms are in categories. You know what epimorphisms are in categories. Now tell me, can you prove this that monomorphisms in the, okay, so why are monomorphisms and epimorphisms studied? I mean, what are the generalizations of or abstractions of? What does a monomorphism generalize? Yes, injective maps. So you understand that. So as I mentioned at the beginning of this session, that category theory is sort of an alternate foundation to mathematics. The former one being set theory. While in sets, you are interested in how objects look from an internal point of view. In category theory, you are only interested about the relationships that objects share, right? And it turns out this is a very deep principle in or deep lemma, I should say, in in category theory, that to understand an object, it is enough to know what are the maps coming out of that object or the maps, that is the arrows going into this object. Okay, you don't need to understand how that object looks from an internal point of view, and that is why an object for a category theorist or for us will be just a blob, let's say. There is no internal structure that this object has. We are not interested in that, but the picture is slightly different in set theory. So in set theory, since you know that sets, I mean, this is one of the basic property of a set, that a set can have elements. There is a primitive notion of belonging in set theory. I can say what it means to write that A belongs to B. Okay, so since you have the notion of elements in set theory, you can talk about injections, surjections without any problem. But in category theory, since objects have no internal structure, there is no way to use the same definition for injections and surjections in category theory, right? And that is why we try to find out equivalent ways of defining injective and surjective maps between sets, so that, and that is defined by equivalent definitions, I mean arrow theoretic definitions, definitions which can be given in terms of arrows. Just as we saw that the definition of a monomorphism can be given entirely in terms of arrows, that is, it can be phrased in category theoretic language. Okay, so you know what monomorphisms are, and since you said that monomorphisms generalize injections, can you prove that monomorphisms in the category of sets are precisely injective set maps? So first of all, if something is an injection, is it a monomorphism? I mean in the category of sets. That's easy, right? We'll not get into that. This is the easy direction. Okay, so if okay, so fix a map at the beginning. Let f be an arrow from A to B in set. Now if f is injective, then f is monic, that is a monomorphism. Now let f be monic. How do you show that f has to be an injection? You want to show that f is an injection of sets, so what do you need to do? Yes, or equivalently, that if two elements go to the same element, then they have to be equal. So let f of A be equal to f of B for some AB in A. We want to show that A has to be equal to B. We are given the data or the information that f is monic. So assume f of A is equal to f of B for some AB in A. We want to use the fact that f is a monomorphism. So consider maybe let's oops, just a minute. Yeah, so uh, consider a singleton set. This is an object in the category, and you consider two arrows from singleton to A. So tell me something, if A is any set, what is an arrow from the singleton to A? What is it equivalent to? Not inclusion, I mean singleton can't be, and it is not necessary that a singleton is a subset of A, right? What is a map from a singleton to a set A? It is just an, I mean, what does a map from a singleton set to A do? It just picks an element from A, right? Yes. So a map from a singleton set to A can also be thought of as an element A in the set A. So what you do is you take two maps from singleton to A. The first map is the one which maps this element star onto the element A in A, and the second map is the one which maps this element star onto the element B in A. And you have this map F. Now tell me something. So let's call, so since we have already used A and B for to denote elements in A, let's write A hat B hat here. You know what A hat does. A hat of star is little a and B hat of star is little b. Now tell me, is it the case that F composed A hat is equal to F composed with B hat? Is it the case? Right, because okay, was this covered in the lecture? as an exercise for this week. Oh, so that means you have submitted, right? Okay. Oh, as class. Okay, then we can discuss. Okay. So F composed with A hat is F composed with B hat. This much we know because the only element that you need to check it on is star, and F composed A hat of star is F of A, which is equal to F of B, which is F composed with B hat of star. So that means these two maps agree, these two compositions agree, and since F is a monomorphism, F has been assumed to be a monomorphism in this category. That means F is a left cancelable morphism. So that means A hat is equal to B hat, which means A hat of star is equal to B hat of star, which means that A is equal to B. Thus F is an injection, right? So there is a further notion of, there is another equivalent way in which you can define an injection, which is again arithmetic in nature, which is the fact that a map is injective if and only if it has a left inverse. Okay, and this particular equivalent definition is also sometimes used, is also very important in category theory. This also generalizes injections, but in a much different way. So a morphism which is left invertible, not just left cancelable, which is left invertible, which means that this morphism, for this morphism F, there is a morphism G in the opposite direction, which is a left inverse of F, that is G composed F is 1A. Such a morphism is called a split monomorphism and sometimes called a section as well. So if it's left invertible, if F is left invertible, then in particular it is also left cancelable, right? Because whenever you have F sorry, just a minute. Yeah, I need to discard these exercises, or maybe I'll leave them for homework. So yeah, so because G composed, yeah, because suppose F composed P is equal to F composed with Q, you want to show that F is left cancelable, which is precisely what that is, you want to show that you can cancel F from the left here, so you can compose with the left inverse G on both sides, and then you get P equal to Q. The point being that every left invertible morphism is left cancelable, that is every split monomorphism is again a monomorphism. So you have three different notions for the, at least in the category of sets. You have two different notions in an arbitrary category of which generalize injections. One is the notion of a monomorphism and one is the notion of a split monomorphism, which is a slightly stronger notion. But all three notions coincide in the category of sets. That is, a map is an injection if and only if it is a monomorphism, if and only if it is a split monomorphism. But we will not get into split monomorphisms any further. We have basically proved that in the category of sets, a monomorphism is precisely an injective map. Now, we can do the same thing for epimorphisms, but the argument is a bit different here. And note that here you cannot use duality argument, because while you know that monomorphisms are, the dual notion of a monomorphism is an epimorphism, you don't know that the dual notion of an injection is a surjection. So duality won't help you here. You have to give an explicit argument here as well in the case of epimorphisms. So this is we are working with the same F from A to B. If F is surjective, then F is epic, right? There is no problem in this. Epic means epimorphism. It's the same name. It's the same name. Yeah, so you know that, so you understand this, right? That if F is surjective, then F is certainly epic. This is easy because epic means right cancelable. So if G composed F is equal to H composed F, provided the compositions make sense, G and H are arrows from the codomain of F, that is from B to some other object C. Okay, so if G composed F is equal to H composed F, then certainly G has to be equal to H. If F is surjective, this is always true, because any element in B can be written as F of A. Okay, That is what the argument is. So this is easy. Now how do you show the converse direction? Let F be an epimorphism, that is an epic morphism, that is an epimorphism, that is an AP, whatever various names you have. So let F be an epimorphism. How do you show that F is surjective? This is very interesting. So we still have 30 minutes. I mean 33 minutes. So yeah. So if you find it boring, I'm sorry, but I need to do it for 2 hours. Yeah. So how do you show that F is surjective if F is an epimorphism? So what you need to show is that the image of F is equal to its codomain, which is B. You want to show that the image of F is B. You have to use the fact that, so you have F from A to B, you have to use the fact that whenever you take any arbitrary object C and any two arrows from B to C such that this compositions G composed F is equal to H composed F, then you always have G is equal to H. This is true for all C and all arrows G comma H. This is what it means to say that F is an epimorphism. Yeah, you are saying something, sorry. Okay, so what you are saying here is you are taking B. I mean, taking the arbitrary set to be B. You are taking one of the G, I mean, one of the arrows, let's say G to be 1B. And what is H? You also need to set what H is, right? To apply the epimorphism, fact that it's an epimorphism, you need to make sure that you are taking arrows such that the compositions are equal, and then you can say that the individual arrows have to be equal, right? So what is your H that can work here? What H can work here? So in particular, what you understand that H has to be equal to F, right? Because if you want 1B composed with F is equal to H composed with F. So yeah, sorry, so what I'm trying to say is H composed F has to be equal to F. That is what you want here. Whatever H is, its composition with F must be equal to F. So that you can apply the fact that it's an epimorphism and conclude that H is 1B. So maybe you can, so I would propose a different argument here, but let's see where it goes. I don't think you can sort of give another map from B to B, right? Because B is an arbitrary set and you don't know what a map from B to B would be. You only know that identity map is a particular map that you can talk about, but you are not sure whether there is a map. I mean, you can't talk about explicitly another map from B to B because you don't know what the set B is, right? So working with B won't help here. That is, this arbitrary object B, I mean this P has to be changed to something else. I would suggest a different thing. So but let's first hear your argument. What do you have in mind? So what do you have in mind? Anything? Any idea? You are getting confused about what to do, or you are getting confused what object you should take? Okay, okay, that's okay, that's fine. I got scared. Okay, so you need to find a C. You need to pick an appropriate C that will help you out. So what I would suggest you here is, uh, so you want, essentially what you want to show is that the image of F is B, right? And what I would suggest you is you take C to be equal to this set, B mod it out by image of F. I think this will work because what I'm doing is I'm taking a set theoretic quotient of B by the image of F, right? So what I mean here is I crush the image of F to a single point, and I take and all the other elements are equivalence classes in their own right. I mean, so to obtain a quotient you need to put an equivalence relation on B. So the equivalence relation is as follows, that X is always related to X, that is always true, and X is related to Y if and only if X and Y are in image of F. Okay, so you understand the equivalence relation. You take X and you relate it to some Y if and only if X and Y are both in image of F. So what are the equivalence classes? Everything which is in image, I mean image of F itself becomes a single equivalence class, and every singleton which is not in image of F, that is an equivalence class. Okay, so you understand what I am doing. So this is your B, let's say, and maybe I need to write down elements, and let's say this is your image. So what is this quotient that I am talking about? This shaded portion, this shaded region becomes a single element, and all these elements which are not inside the image are elements here. Is it okay? Okay, just a minute. কথা বলো না তো এখন. Yeah, so this is my B mod image of F. Now you give me the maps which can help you, which can work here. So first of all, is there a canonical map from B to B mod image of F? Yeah, there are sets, but is there a canonical map from any set to some quotient of it? So suppose X is a set and you take some equivalence relation tilde on x, take a quotient of x modulo tilde. Is there a map from x to x mod tilde? What is that? Yes, yes, A to its equivalence class. So we do have a map here as well. Which is, let's call it pi. Okay. And we want to, we want the other map, right? Now tell me what the other map can be. Yeah, am I missing something here? No, I guess. No. Yeah. Yeah, I guess. Yeah, I'm missing something here for sure, definitely. But I don't know what. Because the other map needs to be defined properly. Oopsie. I think I made a mistake here somehow. I'm sorry for that, but so pi is one map, pi composed with f. What does it do? It sends any element A to the equivalence class of A. Yeah. To make sure that something composed with f is equal to something composed with f. Yeah, I just can't give an example of a canonical map now. That is the problem. Oh, okay. You take the other map to be the constant map. So as I said, the image of f, which was a subset of B earlier, now becomes an element here, right? So what you do is you send everything in B onto this particular element. That is, you consider the constant map on B, whose the value is the single element which is obtained by crushing the image. So constant map with value image of f. Okay, this might look a bit ambiguous, but what image of f is an equivalence class. It's an element in the quotient. So I would write this belongs to B mod imf. Okay, so I hope it's clear now. Now tell me something. Do these compositions agree? That is, does pi composed f equal to this constant map composed with f? So pi composed with f applied on an element A. This is pi of f of A. Now f of A, where does f of A lie? It lies in the image of f, right? And if it lies in the image of f and you apply pi on it, that is, you project it onto its equivalence class, this is just the element in f, right? In B mod image f. And constant maplets denoted by C composed f applied on any element A will of course be image of f, right? Considered as an element in B mod imf. Because C is the constant map with constant value imf, right? It's clear, right? Okay. So now we can use the fact that we have an epimorphism. I mean, f is an epimorphism. So since pi composed with f is equal to constant map, the constant map, that is the map we are talking about in the picture, that is why I wrote the constant map. This particular constant map, yeah, constant map composed with f, this implies that pi is equal to the constant map. I should have used a name, that would be much more clever, but yeah, the constant map with value being imf, right? So pi is equal, if pi agrees with the constant map with value imf, what does it say about What does that say about B mod F? I mean B mod image of F. So what? So pi sends every element of B to its equivalence class, and the constant map sends every element of B to the image to the equivalence class imf. They are equal, right? These two maps are equal implies in particular that everything, I mean everything in B goes under pi to emf, and that basically means that emf is equal to B, which implies that B is equal to image of F, and which therefore implies that F is surjective, and therefore you do have the fact that epimorphisms are precisely surjections in the category of sets. Okay, now if you have a question you can ask me, you can write to me later, and I presume that you don't have a question right now. Now so this is this is the last problem, but we again can't discuss about it. So this is, so do you know how a okay, let me ask you this. Can you give me an example of a category in which the underlying objects are not sets? Maybe I'll erase this problem because you need to understand natural transformations to talk about functor categories and all. So we erase this one. Yeah, just give me, can you give? So yeah, so the point is that so far whatever categories you have seen, most of them are usually, I mean the objects in those categories are usually sets with some structure, right? And the arrows are usually mappings. But if you see the definition of a category carefully, it is nowhere written that the objects need to be some sets with structures, right? These are just primitive notions. Whenever you define a category, you say that a category consists of a collection of objects, right? This is the only data you, this is the only, I mean this is the only thing that you know about objects. So an object for you, as I said earlier, it's like a blob. It's like a blob. This is a bigger blob. Yeah, it's like a blob like this. This is what an object for you is. This is what another object for you is, and this is what an arrow means from one object to another object. It's literally an arrow from the first object to the second object. You don't know how the object looks internally. You don't even know whether there is an internal structure to the object. You don't care about all these things when you are talking about category theory. An object for you is just a blob. But most of the categories you have seen, in them the objects are usually sets. So for the example, the category of groups, the objects are groups, which are sets in particular, and group homomorphisms are in particular mappings. But can you give me an example of a category in which the objects need not be sets? So maybe I can put it as a question. Give an example of a category in which objects are not sets. And arrows, that is morphisms, are not functions, that is maps. Can you give me an example of a category? We can talk about various categories. So let's see. So first of all, we can talk about, we can artificially construct a category of our own. So let's say we choose our category to be made up of 3 objects, and you always have the identity arrows, right? This is part of the definition of a category, right? Every object has an identity arrow. And the arrows that you take are, you take some arrow from first object to second object, you take some arrow from second to third, and you take an arrow from first to third. You can check that this is a category. Also you define this composition, that is, if this is F, this is G, you define this to be the composition G composition. You can check that this is a category, and certainly the objects here are just primitive notions. These are blobs, they are not sets. The arrows also are not maps, etc., etc. So this is an example. You can artificially construct many such examples, but a much more powerful and important class of examples are given by partially ordered sets. So even before we talk about partially ordered sets, you know that the category of sets and arrows, sets and functions is a category, right? I mean, we are speaking redundant stuff, but yeah, you know that what set means. Set means the category of all sets and all functions between them. But it turns out that we can even consider a single set as a category. A set X is a category. What kind of category? It's something called a discrete category. What is a discrete category? A discrete category is one in which there are no non-identity arrows. That is, the only morphisms in such a category are identity morphisms, which have to be present, as you know from the definition of a category. A category must have identity arrows for each of its objects. There should be an identity arrow for every object. Yeah, so a set X can be thought of as a category. So the objects of this category are the elements of X, and the arrows in this category are identity arrows, just some arrows, identities. So while a set X looks like this, the corresponding category for us would look like this. So you have identity arrows for every object, right? This is what I'm talking about. This is a discrete category. So a set can itself be thought of as a category, right? And yeah, I should also mention what composition here is, but as you see, since there are no non-identity arrows defining, you don't need to define compositions as such, right? You only need to define compositions of one A, that is identity arrow for an object A with itself, and that you define it to be 1A. Okay, so do you agree that this is a category? The set X itself is a single category. Yeah, again, you can do much more. You can consider, let's say, a group to be a category as well. So this is one example. Yeah, I'm sorry if I'm rushing through it, but I need to finish it before time. So this is example one, and somewhat building on this example, we can also have this category. So a poset, you know what a poset is? Partially ordered set. A poset itself can also be thought of as a category, but it's slightly different from the previous picture. Objects here are again elements of X, So the elements of the partially ordered set are your objects in this category. And what are the arrows? So there is, you consider, you assume that there is an arrow. There is an arrow from the object X to the object Y, if and only if X is less than equal to Y in this category. So you put an arrow from X to Y if and only if little x is less than equal to little y in the poset. Okay, and what ensures you that you can define a composition here? So observe that by definition, for any two objects little x and little y, there can be at most one arrow from X to Y, right? If X and Y are, if X is not less than equal to Y, then there is no arrow from X to Y, and if X is less than equal to Y, then you have an arrow from X to Y. So what this means is that there is at most one arrow from X to Y for every ordered pair X, Y of objects, right? So what ensures you that if you have an arrow from X to Y and you have an arrow from Y to Z, what ensures you that there is an arrow from X to Z, which you can define to be the composite of this pair of arrows? Very good. So was this example covered in course? Okay, fantastic. So transitivity of the partial order says you that there is an arrow from X to Z. And using transitivity, you can therefore define a composition function to harm XZ for every order triple of objects XYZ in the category, right? And what ensures you that there are identity arrows for every object? So if for every object x there is an identity arrow 1x, what ensures you this? So 1x has to be an arrow from x to x, right? What says you that 1x exists as an arrow? Very good, reflexivity. That is, x is always less than equal to x in a partially ordered set. Right, so a poset therefore is a category. Let's talk about one more example. A group G, comma dot can be considered as a category. Now this particular I mean this is slightly different. I mean from the methodology we have been following so far. Earlier for objects we are taking elements of the underlying poset or set, whatever it is, but for a group we'll be doing something different, because here you need to also use the operation given on the group. So it's a category with object being exactly one. I mean there is exactly one object in this category, exactly one object star, let's say, or maybe I'll write yeah, with exactly one object. And what are the arrows in this category? So if there is exactly one object in this category, if you take any arrow, what should be the domain of the arrow and what should be the codomain of the arrow? Huh? Must be same, and that should be the blue object, right? The single object that we are taking. No, we are defining the group to be a category. I mean, we are seeing the group to be a category like this. That is, this is what we are defining it to be. We include exactly one object in the category, and the arrows should be from this object to itself, because this is the only object present in the category. That is, the arrows should be endomorphisms. They should have the same domain and codomain. So arrows are elements of G. So this is quite abstract, right? The elements of the group are being treated as arrows. There is nowhere mentioned that you need to take the arrows to be maps. That doesn't make sense, because the objects can be anything. So the elements here are considered to be arrows in this category. Okay, so what I mean here is, this is your single object in the category, and the arrows in this category are the elements of the group. So little g is an element of the group, little h is an element of the group, what letters are there, L, let's say. All these are elements in the group, and these are being treated as arrows from dot to dot. Okay, now you also need to talk about composition of arrows. So what is composition? I mean, what do you think composition should be? How do you compose two arrows G and L? Keep in mind we started with a group. G dot DL. Yeah, G dot L, right? The usual. So yeah, so let's write it star to avoid ambiguity. So G star L. Yes, you are right. This is your composition. Okay. And I'm not writing the domain codomain of G and L here, because everything is every domain and every codomain is just the blue dot. So all compositions will make sense here. And what is identity arrow? So there is exactly one object in this category, which means that there should be exactly one identity arrow for this particular. I mean, the only identity arrow that we need to talk about is the identity arrow for this blue object, right? Because there are no other objects, right? ওমা কথা বলতে কিন্তু বারণ করছি. Yeah, so what should be the identity arrow for the blue object? Sorry. Yes, natural, quite natural. Identity element of the group. And you can check that this, since E is an, I mean, let's say E is the identity element of the group, and therefore E is the identity arrow for the object dot. You can check that you, since E is an identity element, E is indeed an identity arrow for dot. What I mean by this is that the arrow E satisfies the axioms of an identity arrow. That is, you compose anything with this identity, you get that anything, right? Yeah, that is G composed with E will give you G, and E composed with G will give you G again. So indeed it satisfies the axioms of an identity arrow. So a group therefore can be thought of as a category. And there is something very special about this category. Can you point it out? So you know what isomorphisms are in a category? Of course you know. They are precisely those morphisms which have an no, 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 no. Isomorphisms are those morphisms which are invertible, right? Yeah, maybe we can do this, discuss this next week. We don't have much time, but isomorphisms are precisely the invertible morphisms of a category. That is, those morphisms which possess an inverse. Now, it's not necessary that in an arbitrary category, if a morphism is both a monomorphism as well as an epimorphism, it has to be an isomorphism, because you understand this, you can understand this, see this very clearly, because something is a monomorphism and an epimorphism means that it is both left cancelable as well as right cancelable. But what actually this is not enough to ensure that the morphism should have an inverse, right? Cancelability doesn't in general imply invertibility, right? Because for invertibility you need to find an arrow in the opposite direction. Cancelability just says that you can cancel it from one side, that's all. So a morphism which is both mono as well as AP is sometimes called a bimorphism. And isomorphism is way different from what a bimorphism is. Isomorphism means a morphism which is invertible, okay, that is, which has an inverse morphism. So if from A to B is an isomorphism, if there is a morphism G from B to A in the opposite direction, such that G composed F is equal to 1A and F composed G is equal to 1B. A morphism F which has an inverse is an isomorphism. Okay, so this is what an isomorphism is. Now you can show this easily, that isomorphisms are in particular monomorphisms as well as epimorphisms because they have inverses, which means that every isomorphism is both mono and epi, that is a bimorphism. But the converse is not always true. It is certainly true in the category of sets, and it is certainly true in the category of, let's say, abelian groups. In fact, any module category this will hold, but this is not true in the category of rings. For example, the inclusion of Z into Q, this is both mono, precisely because it's injective, it will obviously be mono, and you can check that this will also be an AP, because this is something called a localization in ring theory, commutative algebra and all that. So it will be both mono and AP, but this is not an isomorphism, right? Because Z forget this as an isomorphism, there can be no isomorphism from Z to Q. Z and Q are not isomorphic as rings, right? Because one of them is a field and the other one is not, right? So this is very important. It's very important to understand the difference between the two notions. Isomorphisms are invertible morphisms. That's all that you know. Okay. For the category of sets, isomorphisms are in maps which are both injections and surjections. But in general, isomorphisms are only defined to be morphisms which are invertible, which have an inverse morphism. Okay. Okay, so please do keep this particular last example in mind. You can yeah. This is what I was saying so far, that since every element, since one of the axioms of a group is that every element should be invertible, right? So what this means, if you consider the group as a category, is that every arrow in this category is an invertible arrow. That is, every arrow in this category is actually an isomorphism. Every arrow is an isomorphism in this category. And a category, any category in which has some objects and arrows, a category in which all morphisms are isomorphisms is sometimes called a groupoid. So a group can be thought of as a single object groupoid. Okay, so anyway, so keep this particular example in mind, because next week we'll see something very interesting. We don't have time to see that today. We'll see that if you consider a group as a category and you take any arbitrary category, let's say the category of sets, you can talk about functors from the first category to the second category, right? And we'll see that a functor from a group, a single group considered as a category as given in this example, into the category of sets is just a group action. So a group action, while a group is a category, a group action is a functor. So we'll see loads and loads of interesting things next week, once you also see what natural transformations and all those are. But for today we will be ending here. So if you, so do you have any questions? Did I, was it very confusing for you? Okay, thank you. Okay, so I'll stop the recording and see you next week.